Today we'll look at 1.6, which is on functions and different ways we can combine them to create new functions. One of the operations we'll talk about is composition. The other operations we'll talk about are pretty straightforward. This one is a little tricky, okay, but we'll look at it. Right, so we can always take two existing functions and we can combine them in some way to make a new function. Okay, the basic ways of combining functions are simply to take two functions and add them, subtract them, multiply them, or divide them. So suppose we had these two functions. Okay, f of x equals x squared, and g of x equals the square root of x plus 1. And I want to combine them together to create a new function. And I'm just going to combine them by adding. I'm going to do f of x plus g of x. If I want to add these two functions together, is there anything that can be combined? Like if you had x squared plus x squared, you could say it's 2x squared. But is there any way I can combine x squared with the square root of x plus 1? What's that? No. They don't combine, so we just write it like that. So this is a new function, f of x plus g of x, created by adding the two original functions. Okay. What if I wanted to combine them with division? Okay, Orlando, what would that look like if I wanted to write f of x divided by g of x? Yeah, just x squared divided by the square root of x plus 1. If there was something we could simplify, we would, but there's nothing we can simplify there.
Because you can't have a square root in the denominator, right?
Well, right. If we were going to write something as a final answer, generally the book would probably get rid of that square root, which we can do by multiplying top and bottom by square root of x plus 1. And then in the top, there's not much you're going to be able to do. It's just x squared times the square root of x plus 1. And in the bottom, the square roots cancel, and you have x plus 1. So that's a good point. This is probably how the book would write f of x divided by g of x.
So if you have a square root, try to rationalize it?
Yep. If you have a square root, we should always try to rationalize it by putting it in the numerator. Okay, and there's more examples on page 58. They go through a subtraction and a multiplication. Okay, so what we want to do is after we combine these functions is be able to identify what's the new domain of our function. Okay, we might know the domain of each of the original functions, but once you combine them together, now you have to take into account both domains to get your new one. Okay, so the domain of the new function that is created, it's basically all the numbers that belong to the domain of both of the original functions. Okay, so it's all the numbers, all x's, such that x belongs to the domain of the first function, f of x, and also the second function, which we call g of x. And generally, that's most of the time what you have to worry about. Okay, just pick values that are in the domains of both original functions. But when you combine functions using division, you can create more restrictions than you originally had. Because once you divide, what do you have to be careful about the denominator? What don't you want to happen there? Marina? You don't want it to be 0. So there might be some additional values that worked in both original functions. For example, looking at f of x divided by g of x, I can take -1 and square it. I can take -1 plus 1, get 0. Square root of 0 is 0. But once I divide f of x by g of x, -1 is no longer in the domain of that function. Because if I did -1 plus 1, I'd have a 0 in the denominator. So I created an extra thing I had to be careful about here.
So then your domain would end up being all real numbers except -1.
Well, that's part of the restriction. The other restriction is with the square root. Remember, we can't take the square roots of negatives. So with the square root part, we'd want to make sure we say we pick all numbers greater than or equal to -1. Okay, that works for the square root part. But then we have to cancel out -1 because of the denominator. So the domain of f of x divided by g of x, all real numbers greater than -1. Okay, we're going to go through some examples with domain in a minute. Okay, so with division, make sure you don't ever have the denominator equal to 0. If that happens, you need to take that value out of your domain. Okay, and those are really the only two things you've got to be careful with. Make sure you're never taking the square root of a negative. Make sure you're not going to divide by 0. Pretty much everything else we're going to do for functions will work fine, except those are the two things you've got to be careful with. First thing we'll do is find the domain of each of these original functions, and then I want to add them together and find the domain of the new function. Okay, so with square roots, we want to make sure that the radicand is never negative. So what kind of values do I need to pick for the domain of f of x to make sure the radicand is never negative? It can be 0, it just can't be negative. Orlando? -3. So I want to know all the values that I'm allowed to use.
Anything greater than -3.
Yeah, anything greater than -3. Does everybody agree with that? Yep. Greater than or equal to, which is going to change. Instead of using a parenthesis, I'm going to use a bracket. Anything greater than or equal to -3. What about my domain for g of x? What kind of values do I have to pick there, Michael?
Greater than or greater than 2.
Yeah, greater than or equal to 2. If you get stuck, try some numbers. Try 0. Nope, can't do 0. 0 minus 2 is -2. 1. Nope, 1 minus 2 is -1. 2. Yeah, that works. As long as you pick any number 2 or higher. Now I'm going to find the new function, square root of x plus 3 plus the square root of x minus 2. There is really nothing you can do to combine that. But what's my domain of f of x plus g of x? We have to pick x's now that satisfy both of these at the same time. Nick?
Greater than or equal to 2.
Yeah, 2 to infinity. 2 to infinity, if you want to think of it this way, even though there's an infinite number of values in each domain here, 2 to infinity you can think of as a little bit more restrictive than -3 to infinity. It's kind of hard, kind of weird to think of it that way, but that's the more restrictive domain, 2 to infinity. Okay, let's try f of x divided by g of x. So we have square root x plus 3 divided by square root x minus 2. And what do I need to do here just to clean that up algebraically a little bit? Yeah?
Multiply by the square root of x minus 2 on both top and bottom.
Yeah, we'll multiply by the square root of x minus 2 on top and bottom. Now, if we wanted, we could combine these into a single square root in the numerator. It's not necessary. I want to leave it separate for now.
What would it be if you combined it? Would it just be x plus 1?
You'd be foiling it. It'd be x squared minus 2x plus 3x minus 6, all under a square root. Okay? But for this problem, it's not important that we combine it because all I really want to know is the domain. Okay? If I was asking you to write the final function in simplified form, then we could do that out. Okay, but for this problem, I'm not concerned about foiling that out. Okay, what's my domain here? It's going to be similar to the last one, but not quite. We've got to be slightly careful here. Yep.
It's all real numbers greater than 2.
Yeah, now it's strictly greater than 2. Okay. We know 2 to infinity works for the functions themselves, but once we introduce the division, there's an extra restriction. 2 is no longer in the domain. Let's try this one. This time we'll use the calculator to help us out a little bit. Okay, we'll graph and find the domain and range of absolute value of x divided by x. Okay, so we got absolute value of x divided by x. Any thoughts on one value that you can think of right away that's not in the domain?
0.
Yep, 0. Your function is absolute value x divided by x. In fact, 0 is the only value that's not in the domain. Okay, so let's go zoom 6. And that's what we get. We basically get a line y equals 1 to the right of the y-axis and a line y equals -1 to the left. It's because you're dividing two things that are almost the same. Like if you divided x by x, that's 1. Well, the absolute value part makes it so that, let's say you let x be -10. If x is -10, you end up with absolute value of -10 divided by -10. That's 10 divided by -10, which is -1. Any negative value for x is going to come out to -1 for y. Any positive value for x, like 7, absolute value 7 divided by 7, that's 7 divided by 7, or 1. Okay, so my domain there is all reals except 0. Okay, so a couple ways. One way to write it is like this. -infinity to 0, not including it. That symbol, that's the union symbol, meaning there's another interval as well. From 0, not including 0, to infinity. And what about my range here? The range is very restricted. In fact, this is going to be the first problem. We're going to be able to list every single value in the range. We're not going to need an interval. Yeah?
It's just going to be 1 to -1.
What is it?
Well, all numbers less than or equal to 1. And no, that's not.
Yeah, it's not a range here. It's not all numbers between 1 and -1, because like 0.7. 0.7 is not going to be in the range, or -0.2 is not in the range. The range is very small here.
Just 1 and -1.
It's just 1 and -1. No. So we can actually list all the values. Every single y value in this problem is either going to come out to a 1 or a -1. Those are the only two choices. Any question on that? Okay. So let's move on to another way we can combine functions, which is composition. Anybody remember composition from Algebra 2? Okay, well, let's take a look at it. Just another way to create a new function. When we do composition, we'll do it with functions. Then I'll also give you some just simple numerical exercises to try, really basic calculation stuff. Okay, so suppose we had these two functions. G of x is the square root of x. F of x is x squared plus 3. And I want to find that. The way you pronounce it is g of, and now you say what's inside, f of x. G of f of x. This is exactly the same thing you do with a number. Like if I said to find g of 3, all you do is take 3, plug it into the function that's g, and simplify. Well, what I want you to do here is take f of x. That's what I want you to plug into the function g. So this is f of x, and I want you to plug that in to the function g. So we're going to be finding g of x squared plus 3. Any question on what we're finding?
Why wouldn't it be square root of x squared plus 3?
Well, now we're going to we still have to evaluate it. I haven't plugged x squared plus 3 into the function yet. But when I plug it in, that's what it will be. So now I want to find g of, fill that in. That's f of x. So it's the square root of, now change your variable to what they want you to plug in. Usually it's a number. In this case, it's a function. And that's g of f of x. Any question on that? Taking one function, plugging it into another. We'll talk about domain in a little bit. That's can be a little tricky, but we'll try to make it simple. Now I want to reverse it. I just found g of f of x. Let's find f of g of x. So what am I really finding? F of what? What's going to go inside my parentheses? It's g of x. I just want to know what g of x really is. Shannon? Yeah, it's f of the square root of x. So now you're going to take square root of x and plug it in for the variable in the function f. So the function f is x squared plus 3. So I have the square root of x. And I just filled in for x. Square it. Plus 3. Anything I can do there to simplify that? Yeah?
Technically, it would just be x plus 3 because the square root and the square cancel.
Yeah. Those square root and square cancel out. Now, this is a line with a slope of 1, y-intercept of 3. But you've got to be careful with the domain here. The domain is not all real numbers. Okay? We had a square root in there that disappeared as we did the calculation. But that square root is still important when we talk about the domain.
So because if you have that square root there, it has to be, the answer can't be negative. And x
Right.
can't be negative.
And watch what happens if you graph the square root of x. Okay, now put that in parentheses. Square it. And then do plus 3. Okay, we know that the square root and the square are going to cancel out. But the calculator will graph it correctly if I type it in that way. It will not graph, at least I hope it doesn't, the negative part. Okay, so it's starting the line at the y-axis and only going to the right. Versus if you just show me this on paper, I don't know how you got to that point. There was some stuff before it that was important that affects the domain. And we're going to talk about that. Okay? Yeah?
So the x plus 3 is the correct answer for that problem, but if you're talking about domain and range, you want to make sure that you know there's a square root there before. Right?
Oh, yes. Yep. You have to look at this, and this helps us figure out what the domain of this is. Yep. So f of g of x is x plus 3. The domain is all real numbers greater than or equal to 0. Okay, I don't think I do the domain on these two. No. Okay, so another way to word it, I don't use this wording as much. I like saying g of f of x because then the way you pronounce it is the order you write it. But if you see in the book composition of f by g, that means g of f of x. I find that confusing because now the way you're saying it, composition of f by g, is reversed from the way you're writing it. So I'll always pronounce it g of f of x. But this is another way to pronounce it. Okay, and then they also, you might see this symbol in the book. I'm okay with this symbol because the way you write it with this symbol is also the way you read it. This is G composed with F, which means G of f of x. It's like a G, a little circle, and then an F. Again, most of the time I stick with the second notation, G of f of x. Okay, but I just want you to know there are other ways to write this. Okay, how do you figure out the domain once you compose a function? Okay, we already saw that just because you have the final result, you can't just look at that to get the domain. You've got to go back and look at things that happened before that. And the first thing you want to do is look at the inside function. So when I'm talking about the inside function, this is the inside function in this problem, g of x. Okay, and the one above it, it's f of x. That's the inside function. First thing you want to do is eliminate any values that are not in that domain. Okay, so you want to try to figure out the domain of the inside function. Next, you want to look at the final result, the composed function. Okay, now we look at that and we see, are there any additional values that we need to exclude from the domain in the composed function? Well, in the problem we did, no. There are no restrictions on x plus 3. If our composed function ended up being a square root, there could be an additional restriction. If it ended up being a fraction with a variable in the denominator, there could be an additional restriction. But in this case, step 2, we wouldn't even need to do in the previous problem. There are no additional restrictions from the composed function, just restrictions from the original inside function, g of x. G of x was a square root function, so square roots have to be non-negative. So you're allowed to pick any x greater than or equal to 0. And that's why the graph looks the way it does. Yeah?
So you can have a 0 in the numerator.
Of a fraction?
Yeah.
Sure.
So when you're doing your compositions, if you have a 0 in the denominator, that doesn't put any restrictions on your domain, correct?
If you have a 0,
Like if your answer comes out to being 0, is that okay?
so if the final answer came out to a 0,
Yeah.
so then that would just be a horizontal line, y equals 0.
And it would be
Yeah, there wouldn't be any restriction on that because that's just a constant function. There's no variable in it,
so you would just say no restrictions?
at least from the composed function. Now, how you got that answer may affect it. I don't know how you got y equals 0.
Okay, so if, let's say there was a square root in that
Sure.
previously, then you would have to say all real numbers greater than or equal to 0.
Or it depends on what the square root was. If it's like the square root of x minus 2, then it's not 0 in that case.
Yeah.
You just have to adjust your restriction so it's always non-negative.
Okay.
Okay, so let's try just a couple numerical examples. Okay, this one I want you to find f of g of 9. Okay, so to do it numerically, that's easier than algebraically. You just fill in the inside function first, find g of 9, get that value, and then whatever you get for that, plug it into f. And you can do this multiple times. I think in the homework there might be one that's like 3. Like find f of g of h of 2. So you start on the inside, and you just work your way out. Do one calculation at a time. Okay, let's find g of 9. So if you fill 9 in for x in function g, what do you get? Yep, what's that? 3. G of 9 is the square root of 9, or 3. Now I want to plug that value into f of 3. What do I get if I fill in 3 for x in the f of x function? Yeah, go ahead. 4. Okay, so that's just a numerical calculation with composition. And if you just had to find that one value, that's probably the way you'd want to do it. If you had to do this operation maybe 10 or 11 times, you would probably just want to find the composed function itself and use that. And it would simplify your work. So you wouldn't have to do this process 12 times in a row for different numbers. Okay, so let's find f of g of x. So it's f of square root x. Okay, what would that be? F of the square root of x. Oh, Brandon?
Square root of x plus 1.
Yeah, very good. Just the square root of x plus 1. Not asking for the domain here, but there are restrictions we need to be careful with because of the square root. But we'll do some with domain in a minute. Okay, now I want g of f of x. So g of, Justin, what's f of x? X plus 1. Okay, now I want to know g of x plus 1. So how about Carly? If you plug x plus 1 into g, what do you get?
The square root of x plus 1.
Yep. Square root of x plus 1.
But not when the 1 is underneath the square root, correct?
Oh yes, the 1 is because this whole thing gets plugged in for the variable, which is all under the square root. Yep. So make sure you try to make that clear that that 1 is also under the square root. Okay, now we'll do some and we'll find the domains. Okay, first I want to find g composed with f, or g of f of x. Then I want to find f composed with g, or f of g of x. Okay, and we'll write the domain of each. Let's start with g of f of x. Okay, so Andrew, what's f of x here?
X is x squared minus 1.
Okay, so g of x squared minus 1. So now we fill in x squared minus 1 into function g. That's my answer. Square root of x squared minus 1. Okay, now to get the domain. What's step 1? To find the domain, first I have to go back and look at what function? Yep. The inside function. Go back and look at the restrictions on f of x. Okay? F of x was x squared minus 1. Are there any restrictions on x squared minus 1? Orlando? No, that's a parabola, that's a polynomial. The domain is all real numbers. So there is no restriction from the first part. Now the second part is look at your composed function. Are there restrictions on a square root? Okay, what does under the square root have to come out to be?
It has to be 0 or a positive number.
Yeah. So we always want the domain, we want x squared minus 1 to be greater than or equal to 0. Now we'll solve that inequality. And that will tell us our domain. So add 1 to each side. X squared has to be greater than or equal to 1. Which means what? So think about that for a second because we're taking a square root. And this domain might be a little bit different than what we're used to. Yeah?
So when you say x squared is greater than or equal to 1, you're basically saying 1 minus 1 equals 0. And you know that you have to have 0 or a positive number underneath the square root sign, right?
Yes. Yep. You need x squared minus 1 to be greater than or equal to 0. So now, what is this saying about x? How would I finish solving this? Or we could just think about it logically. What kind of number can you square? And the answer comes out greater than or equal to 1. Let's think about some numbers that fall in that category. Yeah?
Any number 1 or greater.
Okay, you could pick any number from 1 to infinity. And if you square it, it will come out greater than 1. Is there anything else? That if you square it, it comes out greater than 1? Yeah?
Anything with an absolute value then?
Yeah, basically anything with an absolute value greater than or equal to 1. So you could write it that way, or if we're going to write it with our interval, we can also pick numbers from negative infinity up to and including negative 1. So like if you take negative 3 and square it, that's 9. So this domain is in 2 parts. Negative infinity to negative 1, and 1 to positive infinity. So there's a gap in the middle. And if you graph it, you could see what that looks like. I'm going to hold off on the graph for now. Okay, there's your domain. Okay, now let's try it the other way and see if the domain comes out the same. Usually it doesn't. Okay, f of g of x. So it's f of square root x. In fact, I think we did one just like this earlier. So I want to plug square root of x into f. And I'm going to get the square root of x squared minus 1. Yeah, we did one just like this. Okay, start with your inside function. Okay, Taylor, is there any restriction on the inside function, square root of x?
It can be 0.
What can it be? Any positive number, and it also does include something else. Positive and it includes 0 is okay. You can take the square root of 0. 0 times 0 is 0. Okay, so from the inside function, our domain is all non-negative numbers from 0 to infinity. How about the final function? Is there any restriction on x minus 1? No. No additional restriction from that, just a restriction from the original function that was inside. Okay, so just write domain 0 to infinity. And if you graph it on your calculator, we've already seen if you type it in like I have in the second to last step, it'll actually do the domain properly. If you type it in simplified in the last step, it's going to draw the full line because you've canceled out your square root. All right, so once we know the domain of a composition, the range isn't that much harder. To find the range, the first step is to find the domain. And then step 2, you just have to reason through and use a graphing calculator to help you visualize it. That's very helpful with the range. To determine what values are going to result if you fill in the domain for x. Okay, so plugging your domain in, what kind of range, what kind of output values are you going to get for y? Okay, so let's find the domain and range. You know what, for this one, we're just going to do it one way. If you look in your book, you can see it the other way, but let's just do f of g of x. Just do it that way. Okay, so I want f of x minus 3. What's going to be my answer when I do that? Filling in x minus 3 in function f. Yep.
Square root of x minus 3.
Yeah, it's just the square root of x minus 3. Okay, let's start with the domain. There's no restriction on the inside function. It's just x minus 3. No problem there. Is there any restriction on the final function, the composed function? Well, Brian?
Yeah,
What does x have to be in this function in order to make this work?
it has to be greater than 3.
Close. Not greater than 3.
Oh, no.
No, you're closer with greater than. Yep.
Greater than 80%.
Greater than or equal. Yep. We have to include 3 in the domain.
Don't you need negative three?
What's that?
Those things?
Yeah, it is 3. You can't go any smaller than 3. If you try 2, it won't work. 2 minus 3 gives you a negative. Okay, now we want the range. Okay, so what I want to do is I'll make a graph of that. And there's not really a lot to be careful of here. There's nothing that canceled out funny, like a square root and a square. So I can type in the final function, the square root of x minus 3. Okay, let's look at the range. Okay, x minus 3, that's all under the square root. Okay, it's starting at 0 for a y value. And how high is it going to end up going? As x keeps going, y, yeah?
Infinity.
Yeah, it goes to infinity. Y is just going to keep going up. You're just going to keep taking the square root of a bigger and bigger number. So the range is 0 to infinity. To see it the other way, g of f of x, I'll leave that. That's in your book. Okay, the next part, it's a little tricky because you kind of have to reason it through. They give you the composed function, they give you one of the original, and you have to find the other original. Excuse me. Okay, so they're giving me f of x, they're giving me g of f of x. I want to know g of x. So that if I compose them in this way, I get that as the answer. Anybody see what g of x would have to be? And if we could just try it and see if it works, and if it doesn't work, then we can make an adjustment, try to fix it. Yep.
AX.
Yeah, g of x equals ax. And now you go through the composition. G of x squared. That's plug x squared into function g. So you change your variable to x squared, and you get a x squared. And that's exactly what we wanted. So g of x is the function ax. So it's a little tricky to think through, but that's how you do it. Yeah. Okay, so our next one is g of f of x equals x squared plus k, using the same starting directions. What would g of x have to be here? So when you do that composition, f of x is x squared. You're going to plug x squared into something that you need to tell me, and I want to get x squared plus k is the answer. Yep? Well, if it's just k, then we don't have a variable, so there is nothing to plug into here. So x squared has to get plugged into something, but the k is part of it. You do need the k.
X plus k?
Yeah, x plus k. Now when you fill in x squared for the variable in function g, you get x squared plus k. Yep. So that's basically, those are transformations. We just wrote a transformation of a parabola, shifting it up k units, or down if k was negative, as a composition of two separate functions. Okay, so that's what the first part of this was, writing transformations as a composition. The first one was a scale factor, vertical. We stretched it up and down. And we wrote it as a composition of two separate functions. Okay, we can also, let's make that a little bigger. If you plug in a negative for x. Change all your x's to negatives. Let's see what happens when you do that. Okay, so what I'm going to do is fill in a negative. And I don't want to write it as 3 minus x, even though you might think that's more simplified, because you always have to keep the x first in order to recognize the transformation. So what I'm going to do is this. I just factored a negative 1 out. If you do the distributive property, you get negative x. Negative 1 times negative 3 is positive 3. And now what happens when you square it, you square each part separately. Negative 1 squared is 1. That cancels out. And you're just left with x minus 3 squared. What's the difference between x plus 3 squared and x minus 3 squared? If you were to graph those. Yeah?
Well, the y-intercept for the first one is positive 3, and the y-intercept for the second one is negative 3.
The y or the x?
I'm sorry, x.
Where it crosses the x-axis. Yeah, it's symmetrically spaced. 3 units. The intercepts are 3 units on each side of the y-axis. And since it's symmetrically spaced, what we just did is reflected it. So anytime that you fill in a negative, just make all your x's negative in a function, that causes it to be reflected over the y-axis. We kind of talked about that yesterday, but this actually proves it with a parabola. If you make x negative, it flips it over the y-axis. Okay, so this is in your book. You don't have to copy it down if you think you understand the idea, but it's starting to extend transformations to all the functions in general. Okay, we did them with parabolas. This is kind of a summary for, generically, other types of functions. Okay, so if you want to vertically stretch or shrink any function, you just stick a number in front of it. That's it. So if I wanted to take a function like this and vertically stretch it, just throw a number in front of it bigger than 1. If I throw in a number like 0.5, that would compress it. Okay. The next one is shifting up and down. If you take a function and you add or subtract a number on the end of it, that will shift your function up or down. So even though we haven't studied square root functions in depth yet, if I gave you something like that on the test, you should be able to tell me that that's going to take the square root function and I might even make it simpler. That'll take the square root function and shift it up 4 units. Or if I made it minus, it would shift it down. Okay, adding or subtracting a number inside the parentheses, that's going to cause shifting left and right. Okay, so my hint to not get confused about that is cover up the minus sign and look at what comes after it. If it's positive, shifts right. Here you'd have to think of it as minus a minus h. Cover up the minus sign, that's a negative h. It shifts left. Okay, so adding or subtracting inside moves it left and right. Reflecting in the x-axis, that's when you put a negative in front of the entire function. Reflecting in the y-axis, that's what I just did with you. Change your x values to negative x's. So the difference between the last two is something like this. Let's say I did the square root of x, that's your basic function. That would be reflected over the x-axis if you put the negative in front. This would be reflected over the y-axis if I put the negative inside. Okay, any questions on the transformations, where you put a number and what effect it has on a function? Okay, so I'm not going to go through this one right now because we have one other thing I want to finish up. But in the homework, they're going to give you a picture, and they're going to ask you to do a transformation to it. Okay, you don't have a formula for this. It's just a graph. So if they said to reflect it, you're not going to be plugging anything in and making x negative. You can't. Just try to sketch it the best you can, reflecting it, maybe something like that. That's all you'd have to do. That's a reflection. Okay, if they asked me to take that function and translate it up into the right 1 unit, so I'd just go up into the right, and there's my new function, translated up, right, 1 unit. There's no algebra to do, it's just drawing a picture. And so this one, they're actually asking me to take the function, shift it to the left 1 unit, then double all the y values. So if a y value was at 2, it goes to 4. If it was at 0, it stays at 0. And then they want me to take that result and shift it down 3. Okay, so it's just practicing transforming a function without a formula. Okay, this will be the last one that we do. Okay, this is in your book. It says that you have a spherical balloon, okay, and it's being inflated. So this is a problem where the radius is constantly changing. It's not a fixed size. And the radius is changing at a rate of 2 inches a second. We're going to assume, to simplify it, that the radius is 0 when the time is 0. And that doesn't really make sense, because if the radius was 0, you don't have a balloon. But it simplifies the problem. Okay? I want to find an algebraic representation for v of t, the volume of the balloon as a function of time. Since this balloon is constantly being blown up, its volume is changing every second. So I want a formula that if I said to you, what's the volume of the balloon at 23.5 seconds, you could tell me. And then we could use that formula to find the volume after 5 seconds. Okay, that's easy. But coming up with the formula is a little harder. First thing we're going to need is what is the volume of a sphere. Okay? And the book gives you that. The volume of a sphere is 4/3 pi r cubed. Okay, any questions on that? Okay, next thing I want to do is come up with a formula for my radius. My radius as a function of time. So my radius is increasing at 2 inches per second. So how would I calculate my radius if I know the time? What would be the formula? Yeah? 2t. The radius as a function of time is 2t. So 5 seconds, 5 times 2, my radius is 10. Any questions on that? Okay. Now that we have a formula that calculates the radius, we're just going to fill it into the volume formula. It's kind of like composition, plugging one function in for the variable in another. Okay, and you get v equals 4/3 pi times 2t cubed. And you do that out, 2 cubed is 8. 8 times 4 is 32. Or if you do it in 2 steps, it's 8t cubed, and then just do 8 times 4, and that's where I got the 32. Now they ask for the volume after 5 seconds. You just fill 5 in for t and do it up. But this is the volume as a function of time. Okay? It's composition. Okay, so on the right, I put up the homework. It's on page 66. Okay, it's 1 to 3, 6 and 8, 13 to 15, 22 to 25, 32, 40, 44, 57, 63. I think problems like 22 to 25, it's one big problem with basically several parts. Same with 13 to 15. Okay, so we'll take a look at that tomorrow.